This is Math317 Operations Research Lecture round 25. What I want to do today is get to, if not the proof of the fixed point theorem, at least the setup of all the stuff that we need. And the biggest thing that we're going to need is a different type of coordinate system than you've seen before. And so in the plane, what should be the dimension of a plane? 2. But we're actually going to use something with 3 coordinates. And the reason we can do this is because we're going to have an additional constraint, very similar to the weights when we had multi-objective functions. The sum of the weights is 1. We're going to have the sum of the coefficients of our 3 vectors is going to be 1. So we really do lose a degree of freedom. We're going to concentrate on the triangle. Why are we going to concentrate on the triangle? There should be some reason.
We've already done Sperner's lemma on it.
Well, we've done, but why are we focusing on a triangle? Aren't there other shapes we could look at? We could look at something nice like this. Yes.
Should you cover any plane with a triangle?
So one thing is you can actually tile a plane with triangles, which is nice.
It's the smallest n-gon that actually has a volume.
So it's the smallest n-gon that actually has, the smallest 3-gon that has a volume. It's very easy to work with. It generalizes nicely. We don't need 4 points. We don't need a square for 3 dimensions. 3 suffices. We could use a circle, but that's going to be much harder to work with. Our coordinate system is going to be, this will be the barycentric coordinates. So this will be V0, V1, and V2. And we will be continuing our tradition of starting our count with 0. And the claim is, you give me any point in here, and I can write that point as T0, V0 plus T1 V1 plus T2 V2 with T0, T1, T2 greater than or equal to 0, and T1 plus T2 plus T3 equals 1. So I can represent any point in here uniquely. Okay, that should be proved. Which places will be the easiest to work with? Corners. So here, this is going to be the point 1, 0, 0, and there shouldn't be any other way to get it other than 1, 0, 0. If you want, what would be a really good choice for the vector V0? Yeah, just the 0 vector. It would be a really good choice for the vector V1. 0, 0, 1. What about V2? There's actually 2 natural choices for V2. What kind of triangle would you like?
I would say right.
So that is one of 2 possibilities.
Equilateral.
Equilateral. So this is the Coke and Pepsi. Okay. How many people want right triangle? All right, so we have 2 hands up. But at least it was an enthusiastic second. Okay. How many people want equilateral? So equilateral tends to win. Okay. It doesn't really matter. What's the advantage of equilateral?
There's functionally no difference.
There's really no difference between them at all. It has a little bit nicer symmetry than a right triangle. So I would say for that reason the equilateral is fine. But this then suggests a really good question. How much does it matter which realization we look at, which choice we make? So imagine we have 2 different objects. And we understand one. Do we understand the other? So let's imagine we have, one of our spaces is going to be very nice. Let's say it's a triangle. And then maybe we have a circle over here. And we have some map, a continuous map from the triangle to the circle. If we understood functions and fixed points on the circle, can we get them on the triangle or vice versa? So we'll assume the function has an inverse. Which do you want to work on, the triangle or the circle? Triangle. So let's say g is a continuous function from the triangle to the triangle. G has a fixed point x naught. So g of x naught is x naught. Okay? We want to try to find functions from the disk to the disk and see if they have fixed points. Can you give me a function from the disk to the disk that will have a fixed point? So remember, g is going from the triangle to the triangle. Yes?
F of g of f inverse at some point in the circle.
So f composed with g composed with f inverse. F inverse takes us from the disk to the triangle. G then takes us from the triangle to the triangle. And then f takes us from the triangle back to the disk. So this is going to be a map from the circle to the circle. Okay? And so if there's a fixed point here, x naught, if f is a one-to-one and onto map, given any point in the disk, there's a unique point that's sent to it, and two different points in the triangle can't go to the same point. We can find a point that goes to x naught. What point do you think in the disk goes to x naught? I'm sorry?
F of x naught.
So if we take f of x naught and apply f inverse of f should just be returning us to where we were. So if I take the point f of x naught that gets mapped to x naught, g then leaves it fixed, and then f brings it back. So if you go through the calculation f composed with g composed with f inverse of f of x naught, you get back f of x naught. So if we could prove that every function that's continuous from the triangle to the triangle has a fixed point, if we then start with a function on the disk, we should be able to prove that any function on the disk that's continuous from the disk to itself should have a fixed point. And we should basically be able to reduce studying the disk to studying the triangle. It all comes down to, do we have a nice pair of functions f and f inverse? You know, these are supposed to be one-to-one and onto. And the problem is these are often very difficult to find. It turns out in complex analysis, it's proven that these functions exist in a great variety of cases. And not only do the functions exist and they're continuous, but they're actually continuously complex differentiable. And so the big result, which we will not be doing in this class, is the Newman mapping theorem. So when I do complex analysis, it normally takes between 1 and 2 weeks to prove this. This is one of the longest theorems you get in an undergraduate education. And the problem is there's a lot of technical results you need from advanced analysis. This is not the class to do this, but I just want you to know that something like this exists. And it basically says if you have a simply connected set that isn't all of C, then there exists a infinitely differentiable complex function f from your set to the unit disk that is one-to-one and onto. So truly amazing. So you give me any strange set, you know, as long as it's not too bad, you know, it can't have holes in it. You give me something like this, and there is an infinitely differentiable map between that and the unit disk. And if the boundary is nice, you can actually even write down explicitly what that function is. This is, I believe, the only homework problem I refused to do when I was an undergraduate. I was taking a graduate level class in mathematical physics, and one of the problems was to take something like this, or maybe a little bit worse, and explicitly write down what was the function, including what it does on the boundary. And I looked at what my homework average was, looked at how many points that homework problem was, and decided it was not worth going through all the details. But there is a formula that allows you to do that. Many of our theorems are just existence theorems. So we don't need to know explicitly what it is. But if you want to do calculations, it's wonderful when you have something that's explicit that will allow you to translate information from one spot to another. So this is the big idea that's going here. You may have seen stuff like this in an algebra class. How many of you have taken an algebra class? So I think it's sometimes, you might write it as, here's S, T, T. I'll try to use the same notation. So I'll have some function phi from S to T. I'll have phi inverse coming up from T to S. I'll have my function G going from S to S. And then, oh no, I'm calling this one F. And I'll call this one G down here. And so the idea is going like this should be similar to going like that. So how many of you have seen pictures like this? Okay, so if you've seen pictures like this, this is essentially what's going on with the different spaces. And the hope is that if you understand one space, you can pass that knowledge on and study another space. We've seen other examples of this before, where it's sufficient to understand just one thing. So does anybody know any other experiences from your, either this class or from other classes you've taken, where if you can study and understand something in one setting, you get a whole slew of related ones with very little work?
I guess P versus NP.
Okay.
Reducing problems in NP.
Great, so P versus NP, that if you can solve this one problem, it's equivalent to solving all these other ones. So an algorithm to solve one is equivalent to doing an algorithm that will solve something else. And unfortunately, the main use of this is to show that whatever you want to study, you can't. That you basically, whatever you're interested in, it's equivalent to all the other hard problems. Good. What's another example of something you've seen?
Linear algebra basis.
Okay. How was that an example?
So if you can understand what happens to the basis vectors in the linear transformation, you understand what
Good.
happens to all
So we
vectors.
just have to understand what the matrix does to the basis. We write a general vector as a linear combination of the basis vectors, and then we get it from there. Another example is logarithms. People's jobs used to be to compute tables of logarithms. Other people's jobs were to check the computations of people on tables of logarithms. And you can imagine that there were people who checked the people who checked. People also calculated digits of E, and people would check digits of E, and then they say, you're actually wrong in the 500th decimal place. All of your calculations from that point onward are wrong. What is the best base to compute for logarithms? Okay, so I hear base 2. Why base 2? Because you could put it into a computer. Now, if you think as to when these tables were being created, probably base 2 wasn't winning. What base would win? Base 10 has a natural advantage. We have 10 fingers. We like to count on our fingers. What other base would have a natural advantage? E. So the two most common bases that people would look at would be base 10 and base E. And if you can do one base in logarithms, you're using the change of base formula, you get every other base for free. So this is the power of being able to do one good calculation and then have some kind of conversion. That's exactly what we're doing here. We're studying the triangle, and once we know what's going on in the triangle, we understand everything about an object that's equivalent. What does it mean for an object to be equivalent? It means we have an invertible one-to-one onto map. I actually don't have to say invertible, it's redundant. Once it's one-to-one and onto, that does imply that's invertible. So another example is, how many of you have taken a stats class? Okay, what is the most important distribution in a stats class? I'm sorry? Did anybody say anything other than the normal who was not trying to be a smartass? So everybody agrees who's taken a stats class that the normal is the most interesting. So you would say the normal, you would not say a normal. So if you're saying the normal, which is the normal that you're talking about? Mean 0, variance 1. Or if you want mean 0, standard deviation 1. Why is it enough to just understand what's going on for the standard normal? Well, if we understand what's going on for the standard normal, we can convert to any other normal distribution. So in the old days, there used to be tables in the backs of stats books with values of the normal distribution, the probability of being this large or larger. And they would only tell you what these values were for the standard normal. Because if you understand for the standard normal, you understand it everywhere. So what we're doing is, again, I want to just really emphasize the big idea that's going on here. Study one example to death, and then show that everything you care about is equivalent to that. So you don't have to keep doing new techniques. This also suggests that probably what we want to do can't depend too much on the shape of the boundary. Okay, so we want to study these barycentric coordinates. So as a nice exercise, you want to prove that you can't represent something two different ways. Okay, so that's a nice exercise. If you want, you can put in specific values of these. If we had 4 dimensions, it would be t0, v0, all the way up to t3, v3. And the only thing that would change is now the sum of the 4 components would be 1. So we all agree that this point here corresponds to t0 equals 1. What does this point correspond to over here? T1 equals 1. And over here, T2 equals 1. What about the boundary down here? What does that correspond to?
T0 plus T1 equals 1.
So one way to write it is T0 plus T1 equals 1. What's another way of writing it? You did T2 equals 0. And we can do similar stuff over here. So this over here would be T1 plus T2 equals 1, or T0 equals 0. And over here, this would be T0 plus T2 equals 1, or T1 equals 0. Another way of writing T1 equals 1, how else could we write that? I'm sorry?
It's true. Are we using like binary?
So, how else could we say T1 equals 1?
T0 equals 0 and T2 equals
Yeah,
0.
T0 equals T2 equals 0. And over here, this is T1 equals T2 equals 0. And this over here is T0 equals T1 equals 0. Does this look vaguely familiar? Okay, it does not look vaguely familiar. Does this look blatantly familiar? If not vaguely.
It looks sort of like the conditions for Sperner's lemma.
It looks sort of like the conditions for Sperner's lemma. So now that we know Sperner's lemma, let's look at this again. This is T0 equals 1, or T1 equals T2 equals 0. So we try to interpret this in terms of labeling. That's basically saying you have to put a label 0 here. What about T1 equals 1? That's the same as putting a label of 1 here. And this is a label of 2 here. Now on the bottom, we have T0 plus T1 equals 1, T2 equals 0. Basically, we can have T0 and T1, we can't have T2. This should be the same as down here, we only have 0 and 1. Over here, we only have 1 and 2. Over here, we only have 0 and 2. And so what I want to do is I want to try to explain why we're going to look at what we're going to look at. The challenge in a lot of these calculations is figuring out what is the right quantity to study. So there's something that my thesis extends. My advisor said it took 6 months to find the right combinatorial object to study. His postdoc said 9 months. I think maybe the postdoc was working on it for a little bit before my advisor got heavily involved. It can take a tremendous amount of time to figure out what is the right way to view a problem. Once you view the problem the right way, it's everything falls into place. But finding that right perspective is hard. So I really want to take some time and try to motivate the quantity we're going to look at. And that's why I'm going very slowly through just explaining what the coordinate system is, trying to give a sense of how this is going to Sperner. So we're going to have a function from the triangle to the triangle. So f is going to map the triangle to the triangle. So if I have f of some point t0, t1, t2, I get some new point, let's call it t1, 0 prime, t1 prime, t2 prime. Right? So it maps some point in the triangle to another point in the triangle. And we can represent any point in the triangle with one of these triples. what do we know about T0, T1, T2 primes? What do we know about that new point? What must be true? So what do we know about T0 prime, T1 prime, T2 prime? Where does it live?
In the triangle.
So it lives in the triangle, okay, so we know that much. What else do we know about it?
Sums to 1.
Ah, it sums to 1. And we know T0 prime, sorry, T0 plus T1 plus T2 equals 1. So we have two vectors. We have the start, we're at T0, T1, T2, and then we have the end, T0 prime, T1 prime, T2 prime. And our goal is to search for fixed points. So what must be true about a fixed point under F? So if it's a fixed point, not converges,
T0 equals T0.
yeah, if fixed point Ti has to be Ti prime. If not fixed point, there exists an I such that Ti does not equal Ti prime. So I want to associate to every point, to every T0, T1, T2, I want to associate a number. What do you think the values of those numbers will be? So I want to, yes.
Maybe 1 times T0 plus 10 times T1 plus 100 times T2.
I like that, but no. It's a really good thing to try. It would keep them somewhat separated. But what numbers are in play for this problem? Where are we trying to get to? We're trying to get to Sperner. What would be a good number to associate to every point in the triangle? Yes?
0, 1, or 2.
0, 1, or 2. So we want to associate to every point either a 0, a 1, or a 2. Associate 0, 1, or 2 to each point T0, T1, T2. We have to figure out how to do this. Which points is it clear what to do? Are there any points where it's clear?
The corners.
Okay. Well, what should we associate to this point?
0.
That's the coordinate. So we want to somehow associate 0 to that, okay? And we somehow want to associate 1 here, we want to associate 2 here, we want to associate 0, 1 down here. We need to figure out what function can we choose that will allow us to associate 0 here, 1 here, 2 here, only a 1 or a 2 here, only a 0 or 1 here, only a 0 or 2 here. What function would do this? And so what we know is that if you give me any point T0, T1, T2, it's mapped to a new point T0 prime, T1 prime, T2 prime. If it's a fixed point, then they're the same. Let's assume there are no fixed points. You know, our quest is to find a fixed point. If there's a fixed point, is this a difficult quest? No. So assume no fixed points. Assume no fixed points. And now we have to assign labels consistent with our Sperner hooks. So we need to figure out a way to assign labels that will give a 0 to this. And all we know is that T0, T1, T2 is never going to be T0 prime, T1 prime, T2 prime. We need to figure out how to assign a label so that when we start off at the point 1, 0, 0, we assign the label 0.
You could pick whichever direction has the greatest magnitude, so that way 0 always goes to 0, 2 goes to 2, and it'll work. And then if there's a tie, you can just arbitrarily assign which one wins. So you can say that if they're all even, if it goes to 2. If 0 and 1 are even, it goes to 1.
Okay, so you want to say whichever one has the largest
Magnitude.
So when I look at these two numbers, how do I figure which one has the largest magnitude? Or just of these three numbers?
Of the 3.
Okay.
Yeah.
Okay, so one possibility is to just say whichever one has the largest. But if we do that, okay, that's one possibility. Yes.
I'm not sure exactly how we would do this algebraically, but label it the direction in which it's most moving.
So one of the possibilities is the direction it's most moving.
Because that would guarantee that each of the corners gets the right number.
Mm-hmm. The point of this is to see that there's more than one option.
Or you can just take out the minimum. Or like, for example, 1, 0, 0, just take out the zeros. Or wait, no, never mind. That doesn't.
But so the point 1, 0, 0 is moved somewhere, right? The point 1, 0, 0 is mapped to something. And we want it to be given the label of 0. So we've got to be looking at its output. So if you're talking about give them the largest, one of my fears is, well, what if the largest isn't associated with 0? And same thing for the direction of greatest movement. Maybe the one goes down maybe the one goes down a small amount, and one of the other components goes up a huge amount, and you might not get the label of 0. So I need something that's going to guarantee me that this point is going to be assigned the label of 0. And one of the things I can do is I can look at where I start to where I go. So I have t0 minus t0 prime, t1 minus t1 prime, t2 minus t2 prime. So what do we know about this sum? They sum to 0. Because the sum of the t's is the sum of the primes. Okay, they sum to 0. And we know it's not a fixed point, so because it's not a fixed point, what must be true?
At least 1 is non-zero.
At least 1 is non-zero, and we can now refine at least 1 to
At least 2.
at least 2. At least 1 is positive, at least 1 is negative. We can look and see which is the first component that's positive and have that as our label. So the index of t0, t1, t2 is the smallest I such that ti minus ti prime is greater than 0. And let's see if that works. If we start off at the point 1, 0, 0, because it's not a fixed point, it's mapped to something. So the first component has to go down. So if we have the point 1, 0, 0, we have no choice. We have to give that a label of 0. Similarly, if we start off at the point 0, 1, 0, this coordinate, it could stay 0. It can't become negative. This coordinate has to go down. So this would be the first coordinate where something goes down. So this gets labeled 1. And similarly, this gets labeled 2. So now all we have to do is check the 3 sides. Let's just check one side. So let's check, t0, t1, and 0. We look at the first coordinate. The smallest I with a new point is smaller than the old. And so we have t0 prime, t1 prime, t2 prime. Is it possible that both t0 prime and t1 prime are greater than t0 and t1? Why can't they both be greater?
Because then t2 prime would be less than 0.
Yeah, because then t2 prime would have to be 0. This already sums to 1. So if t0 prime beats t0 and t1 prime beats t1, then the sum is greater than 1. So we know t0 prime can't be greater than t0 at the same time that t1 prime is greater than t1. So at least one of these has to be smaller. So all the stuff down here will get 0, 1 as a label. All the stuff here will get 1, 2 as a label. And all the stuff here will get 0, 2 as a label. And so this gives us a nice function. What did we have to assume for this function to be well defined? What are we assuming? There's no fixed points. Again, if the whole purpose of this is to prove that a fixed point exists, we can assume that there is no fixed point and then get a contradiction. What if there was a fixed point? What would happen?
Nothing would decrease and anything would.
Yeah, there would be no way to assign the label. So it's extremely important. We're working, finite dimensional space. There will be a first. And so because there's going to be a first, this function is well defined so long as there's no fixed point. Is it true that there is always going to be a fixed point if you have just a map from the triangle to the triangle? So can you give me an example of a map triangle to triangle that does not have a fixed point? So give me some B for bad that maps triangle to triangle and no fixed point.
You rotate it 120 degrees and then take the point in the center and one of the corners and exchange them.
Okay, so we send f of t1, t2, t3 to just say t2. Oh, sorry. So hard to remember to count with 0. t0, t1, t2, to t1, t2, t0, if t0, t1, t2 is not 1/3, 1/3, 1/3. And then send 1/3, 1/3, 1/3 anywhere but itself. So as long as you don't send 1/3, 1/3, 1/3 to itself, you'll be fine. And as long as we're not at 1/3, 1/3, and 1/3, you can't have all three of these being the same, so at least one coordinate will be different. And in fact, if you have at least one coordinate being different, you have to have at least two coordinates being different. So what's bad about this function?
Not continuous.
Not continuous. So if we have a continuous function, we will have a fixed point. But if the function is not continuous, there's not necessarily a fixed point. This should not be too surprising. If the function is not continuous, you can just define it however you want. In fact, we could send every point in the triangle to 1/3, 1/3, 1/3, except for the point 1/3, 1/3, 1/3, which we then send to some other place. So if you lose continuity, it's clearly not going to be hard to find a function which does not have a fixed point. Okay, any questions on what we've done so far? So we have a new coordinate system. We have a way to assign labels, which is consistent with Sperner's lemma. And now the only thing that's left is to see, can we use this to prove a fixed point theorem? That if we have a continuous function from the triangle to the triangle, there must be at least one fixed point. Could there be more than one fixed point? Give me an example of a function that has more than one fixed point. The identity map. Right? So is that considered a stupid example? Thoughts? Do you like it? It's a good example, but it has more than just two fixed points. It has infinitely many. Can you construct something that has exactly two fixed points or exactly three fixed points? And so I'll leave that as an exercise. Yeah. Something to think about. how many fixed points can you have? What are the possibilities? Is it really only 1 or infinity? If so, this is a lot like linear algebra. There's either no solutions, one solution, or infinitely many solutions. There might be something easier to look at than the triangle for something like this. What might be an easier space to look at? I'm sorry?
Like a line?
Well, line is a different dimension. I would certainly think that's two-dimensional. Circle. So it might be easier to try to look at a function from the circle to the circle and see, can you find a function from the circle to the circle that has 2 fixed points? And then somehow pull that back to the triangle. And again, we're not explicitly writing down what is the map that pulls it from the circle to the triangle, but such a map exists. If you are curious, let me know and I will tell you exactly where to look for the answer. It's one of the great gems of complex analysis, that you can actually write down such a function. All right, so it is possible to have multiple fixed points. We don't know yet if it's possible to have a finite number other than 0 or 1 of fixed points. And so the question is, how do we prove? So prove a continuous f from triangle to triangle has at least 1 fixed point. So I've seen some of you looking at the clock. I am looking at the clock as well and trying to see, do we have enough time to do all of this today? And if so, that we could actually get this whole technical lemma done all in one setting, which is advantageous. Now, if you remember the contraction map lecture we had, contraction maps have a unique fixed point. Those are much stronger maps, where they tell you if you take 2 points and apply your function, they're always closer after applying the function. And in that case, there is a unique fixed point. What can you immediately conclude about the identity function? So contraction maps have a unique fixed point. What can you conclude about the identity function? It's not a contraction. This is one of the no shit moments in mathematics, right? The contraction map, the points have to get closer after you apply them. If you apply the identity, do the points get closer? No, the identity should not be a contraction. And it's nice to have some consistency like this. All right, so let's try to prove that there is a fixed point. We're going to need to use a result from analysis. What result from analysis that we've talked about do you think we're going to need? Nope. I wouldn't call Spriner's lemma a result from analysis. Yes?
Immediate value theorem.
Nope. The Bolzano-Weierstrass, right? There was probably a reason we spent time doing the Bolzano-Weierstrass theorem. We need a little bit from real analysis. So here's the sketch. What I'll do is I will assume we start off with an equilateral triangle, and I'll assume we do the nice divisions. Okay? And so here, I'm dividing this into fourths. The next will be into eighths, then 16ths, then 32nds, et cetera, et cetera, et cetera. So every iteration, you divide the sides into 2 to the n, and you look at all the small triangles. So nth stage, divide each side into 2 to the n pieces, partition the triangle into equal pieces. And we're assuming no fixed point. And that means the index function exists. And what kind of values does the index function take on? So what kind of values does the index function take on?
It could be 0, 1.
0, 1, or 2. Do you think this function is going to be continuous? No. Right? We know the index function is going to be 0 here, 1 here, and 2 here. The index function is not going to be continuous. If you have an integer valued function that takes on more than one value in a set like this, it can't be continuous. The index function is highly discontinuous. But we know for each partition, there is some triangle that has a 0, 1, 2 label. And we'll call that triangle, Tn. So we get a sequence of triangles Tn, and each one of these, if you want, you can write them as a triple. Just the coordinates if you want. Is it true that each Tn is contained in the previous? When I subdivide, will I have a 0, 1, 2 triangle contained in here? The only way I would know that is if I knew that all the labels on this line had to be 0 and 1, all the ones here had to be 1, 2, all the ones here had to be 0, 2. I don't know that. Crap. We don't know where the next 0, 1, 2 triangle could be. It could be when we divide things up later. Something like this, maybe it's now like one of the ones over there, as each one of these gets divided into lots of little pieces. And maybe the next one, maybe this is T1 over here, and maybe this is T2 over here. They don't have to be nested in each other. And the problem is we don't know that the boundaries here satisfy our labeling requirement. We only know the boundary of the original one satisfies the labeling. So we have a sequence of triangles, crap. What can we do to that sequence? We can take a subsequence that converges. If you want, for each triangle, you can associate the center. And the sequence of centers will converge. So there exists a subsequence that converges. So call it T and K. And so these triangles could be all over the place, but they've got to be converging to some point. And so we have a sequence of triangles that's converging to some point C. Each triangle has 3 vertices, right? So we have, we'll call the vertices alpha n, beta n, and gamma n, after the 3 first letters of the alphabet. So we have some sequence of vertices alpha n. Maybe the alphas are coming like this and spiraling in. And on all of these, this is going to be the vertex that's labeled 0. These will be the vertices that are labeled 1. These will be the vertices that are labeled 2. Because on every triangle, because it's a 0, 1, 2 triangle, there's always a vertex labeled 0, there's always a vertex labeled 1, there's always a vertex labeled 2. I probably shouldn't be drawing this continuous, I should have a bunch of dots. It's faster to just draw a continuous line and imagine some kind of path. So along this path, all the labels are 0. And as we approach C, we want to assign the value 0. If we look at the betas, maybe the betas are going like this. And maybe the gammas are going like this. You're getting into this wonderful mess now. But as you approach C, you have 3 ways to approach C. And we want to label C 0, 1, and 2. What does it mean to have a label of 0? Remember, we have f of t0, t1, t2 goes to t0 prime, t1 prime, t2 prime. So a label of 0 means t0 is greater than t0 prime. A label of 1 means t1 is greater than t1 prime. And a label of 2 means T2 is greater than T2 prime. So as we're going to this point, as we go along the sequence of alpha, the 0 labels, we're always going to be along points where the first coordinate is mapped to something that has a smaller first coordinate. In the limit, what must be true about the coordinates for C? So this is the hard part. We now have to figure out what happens in the limit. We've got about a minute to go. So f of alpha n has its T0 coordinate smaller than the T0 coordinate of alpha. Right? That's what it means to have the 0 label. So in the limit, the T0 coordinate of C is greater than or equal to the T0 coordinate of f of C. So if you are greater than 0, then in the limit you may not be greater than 0, but you'll be greater than or equal to 0. So we know that the T0 coordinate of C is greater than or equal to the T0 coordinate of f of C. The same is true for the T1 coordinate, the same is true for the T2 coordinate. So if we have f of C0, C1, C2 goes to C0 prime, C1 prime, C2 prime, we know C0 is greater than or equal to C0 prime, C1 is greater than or equal to C1 prime, and C2 is greater than or equal to C2 prime. But what do we know about the sum of C0, C1, C2?
The same as this.
The same as this sum. So if the sums are the same, what's the only way that we can have this work? All equal. All equal, else the sums are not equal. So if one of these was strictly greater, then this sum would be 1 and this sum would be strictly less than 1. And that finishes the proof with, what, 22 seconds to spare, not even close. Okay? So that is the proof of the Brouwer-Fixed-Point theorem. We were able to do it in a day because we put stuff in the bank. We put real analysis in the bank. We put Sperner's lumber in the bank. But at the end of the day, it's a nice application.